In the previous lecture, we introduced the electric potential, and we saw that it is related to the electric field. V is minus the integral of E dl, or E is minus the gradient of V. And before that, we had already established relations between the electric field and the charge density ρ. So in this video, we are going to look at the relations that relate the electric potential V directly to the charge density ρ and vice versa. The first one is called Poisson's equation. So we start from Gauss's law in differential form. The divergence of electric field is equal to the charge density ρ divided by epsilon naught. And we combine it with the fact that E is also minus the gradient of V. And so the divergence of minus the gradient of V is equal to ρ over epsilon naught. And we can take the minus out. So minus the divergence dot gradient of V is ρ over epsilon naught. Multiply both sides by minus 1, and we obtain nabla square V equal minus ρ over epsilon naught. Nabla square is called the Laplacian operator, and this equation here is called Poisson's equation. With this new formula, we can already update our electrostatics equation summary. If you know the potential and take the Laplacian, then you can get the charge density. So we can go from V to ρ with this relation. Now, before moving on, I mentioned quickly another equation. If you are in a region of space where the charge density is 0, then nabla square V is equal to 0, and this is sometimes called Laplace's equation. This equation is important in electrostatics and in physics in general, and so we have an entire chapter dedicated to it, which we will cover in this class. Now, we're going to write the equation to find the electric potential from the charge density. So suppose we know the charge density ρ, and we want to find the electric potential V directly without going through the electric field. So for this, we come back to the potential from a point charge. Suppose the point charge is at the origin. Last time we saw that the electric potential from a point charge is 1 over 4 pi epsilon naught Q over R. We found this taking the reference potential at infinity. We did it for a uniformly spherical shell and found the same result. If the point charge is not at the origin but at a position R prime, then instead of R, we're going to use the separation between R and R prime, so curly R. If we have multiple point charges, Qi, at different positions, then we can sum the potential from each of them. So we have V equal to 1 over 4 pi epsilon naught, sum for I equal 1 to n of Qi over curly Ri. Again, each time you use this, remember that the reference potential is at infinity. And now we are ready to generalize this to continuous charge distributions, where we replace the sum by integrals. So for a line charge distribution, V equal 1 over 4 pi epsilon naught integral over the line of lambda of R prime over curly R dl prime. For a surface charge distribution, V equal 1 over 4 pi epsilon naught integral over the surface of sigma of R prime over curly R dA prime. And for a volume charge distribution, V equal 1 over 4 pi epsilon naught integral over the volume of ρ of R prime over curly R d tau prime. You don't need to remember all of them, but you should be able to find one from the other. See how they are all related and have the same physical meaning. You know the charge distribution, and you integrate or you sum all of the contributions to the electric potential, which goes as Q over curly R or ρ over curly R. So in the end, this concludes our relationships for electrostatics. We have three fundamental quantities: the charge density ρ, the electric field E, and the electric potential V. And we have established equations to go from one to the other in all possible directions.